Hey everyone, welcome back. Today I spent basically the whole day just trying to do this. Not literally, but yeah, I spent a significant chunk of my day trying to focus this down. I think maybe we'll try and start writing code. I might actually hold off. Actually, I think I might just hold off on writing the code tomorrow because it is pretty late. But I'll just go through what I did, which was essentially trying to focus in. So previously we had defined what eigenvalues and vectors are, right? So for a real symmetric matrix A, actually not for just any symmetric matrix, but for any transformation, there exists a vector such that the output of multiplying or applying that linear transformation defined by some matrix A to this vector yields the same vector but scaled, and the scalar value is lambda, is eigenvalue. So that's what an eigenvector and eigenvalue is. The task was to basically just shove it into NumPy and get the eigenvalues for a few symmetric matrices, and I was like, nah, I'm gonna calculate the matrices myself because I'm a dum-dum, right? Which is where I got into this and was a little bit confused by this. This part is actually just describing why symmetry makes it easier. Not because you can choose the eigenvectors in such a way that they're orthonormal. What I've realized in this is that Q literally stands for a matrix of orthogonal vectors, and if they're chosen orthonormal, A can be represented as Q lambda, which is the diagonals of is a matrix that's a diagonals of eigenvalues times its transpose, and the transpose of the matrix is also its inverse because it's orthogonal, which is why Q transpose Q equals I. Essentially, that orthogonality gives you numerical stability, which I'm not sure what a back transform is, but check residuals is check the error between the original and the new. Essentially, they had a page about why orthogonality can reduce the number of calculated defined algorithm. This reduction in complexity stems from the fact that triac have been leading to faster calculations, especially for larger matrices. Is that really why? Oh no. No, yeah, this is a whole other question as to why they preserve the Euclidean norm, because that's part of why it gets numerical stability, right? That is actually the thing I landed on, and this is where I stopped last. I need to try and understand this. I'm not really sure, because I was trying to understand why do orthogonal matrices preserve the Euclidean norm. And I think part of the problem is the reason I was a bit confused here is because they're doing norms of matrices as well, which I don't know how to interpret the norm of a matrix, to be honest. Or QX, could it be that? Yeah, it could actually be a norm of a vector, right? Because a matrix multiplied with a vector, not the transpose of the vector, because I don't think that's possible, but the vector itself, presuming that okay, I think we have to go back to matrix multiplication. As long as the number of columns match the number of rows for the vector, there you go. I think that would be correct. I was about to say the rows in the matrix matches the number of elements of that, but I don't think that's quite right. That doesn't make sense. Anyways, so that's what got me confused here. But I was trying to figure that part out. It was coming back to our original thing, I keep coming back here and doing the full review. It helps me too, honestly. right? Um, so that's why symmetry is valuable, and there is such a thing as just diagonalizing the matrix directly and getting the eigenvalues that way, which actually I didn't realize. Oh, not this video. There's another video. Where is it? Let me see if I can check my history. Maybe over here. History. There you go. Yeah, this guy.
We are asked to diagonal.
So, it's stupid simple, and it should have flowed from one of the things I realized earlier, which is, I think it's maybe in this chat itself. It's not this. Oh yeah, I think there was a. This is the chat explaining the actual task. There was another one where I just went into eigenvectors. Ah, there you go. There it is. Right, so it's actually peripherally on AV equals lambda V, so which can be rewritten as A minus lambda IV equals 0. And, you know, for a non-trivial solution to exist, this needs to be true. And what I didn't realize is this, obviously, this is just like, you know, for like a 2x2 matrix or a 3x3 matrix, if you just expand that, you just get, like, I think it's a polynomial, and you might actually already have it factorized. But you yield a polynomial that you can factorize, and you can get the lambda values that way. That's what it means to diagonalize the thing. The problem is that for an arbitrary number of, an arbitrary size, it's very computationally expensive. I think so you'll essentially just solve for the determinant equaling 0, right? You get this funky little determinant, and then you know how to do the determinant of a matrix, right? You just expand like the cofactor equation, and boom, you just essentially get what you need to form a polynomial, and it's already preformed. So here in this particular example, you already, because it's already factorized here. I didn't bother to like double check this. I'm trusting that because it just made sense and flowed, right? Because that's the property. And then you can just diagonalize the matrix. That way you get all the eigenvalues, right? And then to go from eigenvalues to eigenvectors, you essentially solve
0.
Oh wait, I'm just gonna maximize this really quickly. Move my head over here. A minus lambda ix equals 0, the 0 vector, right? You just solve for this essentially, and like it's literally as simple as, you know, doing Gaussian elimination with ax equals b. It's pretty straightforward. And that's how you get each different, and you do that with each eigenvalue that you've received in the diagonals, right? And then when the matrix is fully diagonalized, that's when you have your eigenvalues and eigenvectors. You essentially represent it as P being the vector of the matrix of eigenvectors, lambda the matrix of eigenvalues diagonalized, P inverse. Or wait, is that how you represent it? Yeah, PDP, because yeah, PDP inverse. That's correct. So I'm gonna move my face back here into the corner. So that was kind of dumb, and what I then realized is what I'm actually looking at is a more advanced algorithm for the special case of symmetric matrices, where you do a Householder tridiagonalization, which essentially involves constructing reflector matrices repeatedly. And once you have all of them, you can use that. You will yield a matrix that is a tridiagonal, which is its diagonals are filled in and the first off diagonals. So if it's a 3 by 3 matrix, um, it's like 3 diagonals. I don't know how else to describe. Actually, you know what? I do know exactly how to describe it. Boom, right there. This photo right here, that's a tridiagonal matrix right here. So that's where it's at. After that, you do QR factorization iteratively to actually get the final answer. So I do not understand implicit symmetric QR iteration. I do understand to some extent. Basically, there's some manipulation here where you get the new T without actually solving for Q and R. I'm not exactly understanding how that factorization works, but that's essentially the case, right? So going into household or tridiagonalization, I had a whole other chat for that. Oh, no, not that one, this one. Right, just to understand how the steps worked and stuff like that. And I didn't understand it immediately, but I'm going to pretend like I did while I'm explaining it. So essentially, the household reflector, probably named after some dude, is essentially the identity matrix minus 2 times, for a non-zero vector, is the identity matrix minus 2 times the outer product of the matrix divided by the dot product of the matrix. So 2 divided by the dot product of the matrix, which yields a scalar, and then you scale the outer product of those 2 vectors by that and subtract the identity matrix. That's how you get the household or reflector. And remember from our previous episode that the outer product essentially yields a matrix and the inner product is the dot product, right? And yields a value. Really thirsty. I'm gonna drink some water. So I'm gonna try and read the official because I honestly did not understand this the first time, where they're describing an iterator and then I made it run through a couple of examples. I made it run through one example, like a 4x4 example, before I got it. So I'm going to try and see if I can read this and understand it. So, one step at column K. So, in this case, column K is, let's say, 1 for the first step, right? We want to 0 elements below the first subdiagonal. So we have the main diagonal, we have the subdiagonal, and then I think the supra diagonal. I think that's what called. Those are the 3 diagonals. That's what they're called, right? In column K, entries, aka entries from K plus 2 through K. I don't understand why it does n comma k again. That doesn't make sense why it's comma n comma k. The comma n makes sense. Oh, k plus 1 through n. So, okay, form the vector to annihilate. So, annihilation. Finish him. Transform him. No, I'm kidding. That's just had a little Mortal Kombat fun. So, k plus 1 through n of k. The part of the column K below the diagonal element. Choose the target direction. Let E1 be the first basis vector of Rn minus k. I want to reflect x. We want to reflect x onto a multiple of E1 so that after the transform only the first entry remains. Compute So n minus k is, I think this is essentially saying pick the actual first vector, which is all the elements under the, so if you're on step 1, it's not the first row, it's not the second row, because those two will be the main diagonal and then the subdiagonal, and then all of the elements underneath it. At least that's what I'm recalling from the example. We compute alpha, which is the sign of the first element of this vector times the magnitude of the vector, so the L2 norm over the Euclidean norm. Taking the same sign as x1 avoids catastrophic cancellation. Okay, I don't know what that's about. I'm not going down a Googling hole right now. I've been literally just doing that the entire day. So I'm gonna focus on explaining to you guys where I've understood this till. Define u equals x plus alpha e1 normalize vector v equals u over the magnitude of u. So this, I still don't understand. I understand alpha. You know what, let's look up a householder reflector and should double check this on Wikipedia. So I don't know what this is talking about. You're looking for a plane so that the reflection of this plane happens to land directly on the basis vector, in other words. However, for this to happen, we must have a vector v such that x minus alpha e1 this is looking familiar. Okay, I'm just gonna trust this for now, because something that's confusing me here is the fact that E1 is seen to be a vector, and then you construct the reflector embedded into full space, which is, this is fairly straightforward. You just take the identity matrix essentially, and then in the bottom right you shove in your reflector that you have built from the previous step. No, you do, yeah, you use I, because the reflector is defined by I, as we discussed earlier, I minus the outer product, right? So you take the outer product of the vector you just formed, I minus that, and take the, and for, since that's going to be smaller, because the vector you started from was already too smaller than the matrix, that'll be a smaller matrix, so you embed that into the full space matrix, and wherever the values of the reflector don't go, you're just essentially doing the regular identity matrix. And then you just apply the similarity. And you just repeat it, right? Applying the similarity, meaning just do transpose of the reflector times the matrix, the original matrix times the reflector again, essentially. And I think the householder reflector is also symmetric. Not sure about that though. Oh, it's a orthogonal. Oh, it's orthogonal and symmetric. I'm done. Right, so doing edge times edge transpose is pointless because it's just the same vector. The same matrix, I mean. That's why they dropped the transpose over here. Since edge k is symmetric, it says so right here. All entries right of the first super diagonal in row k. Alright, so that's essentially what that is. Now to showcase, see, this is the step that confuses me. How to do householder deflections. Let's just start with that. Just gonna, oh, this is PDF. That's not a very big PDF. Well, actually, let me just open it here like this. The Gram-Schmidt orthogonalization procedure is not generally recommended for numerical use. Yeah, you could have told me that before I tried, before I did the code for it. That wasn't too bad, actually. I think from actually coding it, perspective Gaussian elimination is the hardest. Gram-Schmidt was just hard because it was like I was trying to understand it. I feel like similarly here as well. Okay. I think this is MATLAB. Actually, I don't understand what this concept of cancellation is. Oh god. I don't want to even get into the givens. So anyways, I think I'm just going to go over the householder reflection example, worked example. So I did it for a 4x4 because otherwise it's just done in one step. And just to not have a non-trivial example that I can follow step by step to understand. I think if you do 2 steps, then it's fine, right? So you take the column below the subdiagonal. Sorry, you take the column including the subdiagonal, right? Take the magnitude of that alpha, which is the sine of x1, so it's positive times 2, 3. See, this is the part that's confusing, right? It's saying E1, but E1 is the first vector in the original description over here. And this is why I'm like having a bit of a brain fart here, because if you follow this, it makes complete sense. But then they make a mistake here. Now I can't tell if this is AI generated like mistakes, because here it's x plus alpha E1. So if alpha E1 is just like the first element in the vector, right? That's this is the vector, right? Negative 0.111 and negative 1.111. So taking the first element times alpha, right? Plus that first element itself. So first element, negative 0.111, okay, plus alpha E1, it's already negative, so that plus becomes negative, that part's fine. But then this is not multiplied by 0.1111, because it would otherwise lose the decimal point would jump over 1, and it's not, which is why I'm like, what is going on? And I honestly don't know if this is a ChatGPT mistake or what. Here it's just boom, boom. Right? Which is why I'm confused. And then you just you take the outer product of this vector, I minus that, and you get this. It's pretty straightforward. And then you just embed it in the full matrix. And then you do the so you do edge, A, edge to get A, or the matrix you're going to use to construct the next reflector. And you just keep doing that till you have a fully formed tridiagonal matrix. So that's pretty straightforward. I get that. I just want somewhere to confirm. I'm just gonna do word example householder reflector, just so that I can have mental peace regarding that E1. Let's do that live together. Stat ledger. Let's see if this works. Two outer product B normalized the K by K identity matrix. Oh, this is doing it with complex numbers, right? Even better. Yeah, Hermitian matrix is another thing that's basically a symmetric matrix when we're looking at complex numbers. Because why is this so hard to find? I'm just looking at the images. Oh, what do we got over here? Oh, there's that same one from there. Nope. Ah, someone. So these are 4 ways. I guess I could have just done the Gram-Schmidt process and then move straight to QR decomposition, because they're essentially 2 different things, right? What I don't understand is if I just get any pair of orthonormal vectors, how does the QR? I guess the QR decomp step is the step where you actually get the eigenvectors and values, and everything else is just how you get orthonormal vectors. We try to decompose each column vector in A to a set of linear combinations of orthogonal vectors in Q. We'll try to map each column to a set of orthogonal vectors, okay. Oh, okay. I get it. So that's the unit vector. And that's what it said as well, didn't it? ChatGPT. Right? Form the vector to annihilate. Choose the target. Let E1 be the first basis vector of Rn minus K. We want to reflect X onto a multiple of E1. A basis vector is a unit vector, if I'm correct. Is basis vector a unit vector? That can be used to represent any vector in a vector space. So while standard basis vectors along the x-lines, other bases can be constructed with vectors and unit vectors on the other hand, or simply vectors with magnitude or length of 1. Yeah, that's what I thought. Try to decompose each one as a orthogonal, therefore we will try to map each column in order to map each vector to the orthogonal vectors above. We applied householder reflection to each column vector. Okay, so I'm just going to presume that even though they said basis vectors, which is true, I'm assuming the math essentially works out the same, except at a certain point you're doing some sort of additional normalization of the vector, versus here where if you just pick a unit vector to begin with for your basis vectors. That makes more sense to me. I don't think that's explicitly stated, but that's true. So anyways, going back through this, that applies here. I'm gonna see if it sees what it got wrong here. Because I think that's just like a ChatGPT like math mistake. It's running some code to try. Quick audit. Okay. Okay. This is where I have a problem. I'm still not sure. Let's just adding two vectors, you have to add them where they're at, right? So if I go back here, step 2, this is negative 1.11653. Okay, alpha times E1. Alpha times E1. E1 is just the unit vector, isn't it? right? We just discussed that. So that actually makes sense. Okay. Okay, this actually does track. Never mind, I didn't make a mistake. Right? Because if E1 is just a unit vector, it's 1 plus 3. I was seeing this. I don't know, I guess I was tripping. Right, so anyways, you take that vector, you get alpha, you take the magnitude of that vector, you get alpha, which is essentially the sign of the first element times the magnitude. So that it's still something about catastrophic cancellation. I'm not really understanding what exactly that is. You take u equals x plus alpha e1. E1 is the basis vector for this transformation, right? And you're going to go through all the dimensions, right? So it'll be 1 0 0, and the next one will be 1 0, but it's lower, you know. So I think that makes sense. You get the norm of this new vector. You divide this vector by the norm to normalize it, and then you do I minus 2 times the outer product of that vector to get your Householder reflector, which you embed into the full matrix, and you do the new reflector times the original matrix times the new reflector to get the new matrix for the next step, and you keep doing this till you get an actual tridiagonal. You don't actually, that's how you do Householder tridiagonalization, by my understanding. Hope that's correct. I think that's a good place to stop. I think I'm getting close to actually starting to write some code. I was actually hoping to write some code in this video itself, but it's kind of late. I haven't had dinner and all that jazz. Same old. So I'm just gonna clock off for today. But thank you guys for being on this journey with me. Have a great one.